Last time we developed kinetic energy. I described the experiment that probably resembles the experiment that Emily de Châtelet did, where she dropped objects into dry sand and related how deeply the object sunk into the sand to what the energy of the object was at the point that it arrived at the sand. And from that she concluded that kinetic energy is 1/2 times mass times velocity squared. So that was last time. We have our expression that kinetic energy is 1/2 mv squared for a mass m that is moving at a velocity, actually at a speed v. Kinetic energy does not depend on directions. Remember the experiment that I described? She dropped these pebbles into this dry sand, and again this is my historical rendition of how I can best surmise it must have happened. And the pebble burrows into the sand at distance d. What she found was that the distance it goes into the sand depends on the square of the velocity the rock has when it hits the sand. So from that, she argued that energy must be proportional to d because that's work. Work is force times distance, so it's the friction of the sand on the pebble. And that led to the conclusion then that energy must be proportional to speed squared because the distance into the sand is proportional to the square of the speed at the point of impact. And so now let me describe the rest of my hypothetical du Châtelet experiment. If she were to vary the height from which she dropped it, it would be faster as she goes higher, and it will go deeper as she goes higher. But here's a question. How does the depth that the rock burrows into the sand depend on the height from which it gets dropped? It does go a certain distance. Now increase the height, how much deeper does it go? So that was done, and it was observed that the depth that the rock goes into the sand is proportional to the height from which it is dropped. So you double the drop height, you double the depth that it burrows into the sand. Therefore, if you double the height, you double the energy. So you can write it as the rock's energy is proportional to height. This is a proportionality symbol, these symbols. I don't know if you've seen that before, but you're going to see it now. That symbol means it's proportional to. So if y is proportional to x, that means a graph of y versus x is a straight line. So another experiment that would be reasonable to do would be to drop multiple pebbles of different mass from the same height and see what happens there. It turns out that if you double the mass of the pebble, you also double how deep it goes. So you double the height, you double how deep it goes. You double the mass, you double how deep it goes. You double either one, you double the energy. So there's an energy that's proportional to the mass and the height. When you hold the mass up here, it has a certain amount of energy. It's called potential energy because the energy that the rock has when it is way up there, it's not moving, but it is the potential to move. It's the potential to gain kinetic energy, and so it's called potential energy. And specifically gravitational potential energy because it's associated with there being gravity. If you drop these rocks in a zero gravity environment, they're not going to drop. So it's associated with how much gravity there is. In fact, you might recognize this m times g portion of the expression, in fact, is gravitational force, mass times little g. Kinetic energy is 1/2 mv squared. That's the energy associated with motion. Potential energy is mass times little g times h. That is the energy associated with position. So position and motion are the two factors that determine energy. So you either have a lot of position, like the skydiver, or you have a lot of motion, like the guy who's running from arrows. Drop the rock, and it goes in the sand. Something's transforming here. You have this rock up here with a lot of potential energy, and it transforms into having a lot of kinetic energy when it hits the sand. And then it does a bunch of work going into the sand, pushing sand particles out of the way. So this energy is changing places. When you're way up here at top, you have all this potential energy. It is equal to mass times little g times h. When the pebble gets down here to the sand, it has entirely motional energy, kinetic energy. There's no more distance for it to go. Its energy is 1/2 mv squared. Now that goes into the sand. When it goes down a distance d, it is a distance minus d away from the surface of the sand. And so down here, it goes back to having potential energy, negative potential energy. So if you are below the ground, you have negative potential energy. If you are in a hole, if you're down in a well, you have negative potential energy. M times little g times how deep down you are. And that's the final energy. If I talked about dropping something to the ground, it starts with an energy of mgh. It hits the ground, it has an energy of 1/2 mv squared. Now in this case, the ground is made out of dry sand, and so it digs a little deep into it. And so it has a final energy, which is minus mg times how far down it went. To answer this question, can energy be negative? Potential energy can be negative. Kinetic energy can never be negative. It makes no sense. There's nothing in here to be negative. Mass can't be negative, and velocity is squared, so it can't be negative. But mg distance can be negative if you're at a negative height. Potential energy is relative to some place, usually the ground. So we'll say potential energy is relative. What I'm going to prove to you is that if I calculate the mass of that pebble times 9.8 meters per second squared times the height, it will be the exact same number as if I calculate 1/2 times the mass of the pebble times its speed when it hits the ground squared. And that's called energy conservation. The energy that it starts with is the energy that it ends with. It just changed forms from potential to kinetic. There's a balance there then. The initial energy of that pebble, which was all potential, equals the final energy of that pebble, which is all kinetic. And it equals the final energy of that pebble, which is minus mgd, the final potential energy, plus the work done by the sand with friction slowing it down. We're going to focus on this first statement here, that the initial potential energy equals the final kinetic energy. You start off with a bunch of mgh and you end up with a bunch of 1/2 mv squared. Those are the two forms of mechanical energy. I might emphasize right now that work is not a form of energy. Work is a loss or gain of energy. It's taking energy in or out of the object. I'll show you how that works right now.